Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video going over your Zybooks section 10.8. It's titled Permutations with Repetitions. So in the previous several sections on permutations and combinations, you've been taking a set of n objects that all looked different. You were taking a set of n distinct objects and creating sequences or subsets, permutations and combinations from those sets of n distinct objects. Well, now we're going to be looking at sets of objects where some of them are indistinct or indistinguishable. Some of them are, they look exactly the same, some of these objects. And how many different ways, how many different looking ways can I rearrange objects like that from a set like that? Right. So again, the question is, how many ways are there to scramble the letters in the word Mississippi? So you see M-I-S-S-I-S-S-I-P-P-I. That's 11 objects, 11 letters we're rearranging. But notice the repetition of some of these letters. 4 S's all look the same. 4 I's all look the same. 2 P's all look the same. So the question is concerned about counting different orderings, which suggests counting permutations. However, a permutation is defined as an ordering of distinct objects. Right? The letters of Mississippi have multiple repetitions. They're not all distinct. Like I said, the 4 S's, 4 I's, 2 P's, and 1 M. So a permutation with repetition is an ordering of a set of items in which some of the items may be identical to each other. And then to illustrate this, all right, so you know what? I'm going to go through Mississippi right now. I know they have it down here in the animation, but I'll show you how we're going to count these. And I know it's called permutations with repetitions, but you can count the number of ways to rearrange objects where some of them look the same. You can count them using combinations, and I'll show you. So again, here we have the word Mississippi. M-I-S-S-I-S-S-I-P-P-I. So again, there are 11 letters here, 11 objects. And again, there are 4 that look exactly the same, 4 S's. There are 4 I's, 2 P's, and 1 M. So again, 11 letters, not all distinct. Right, so I can't count the number of different rearrangements the way I used to. Right, because normally, if I had 11 letters, 11 objects, and they were all different, the number of ways to rearrange them would be 11 factorial. But that is not the case here, because if I switch these 2 S's, it looks exactly the same. So it wouldn't be considered a different permutation. If I switch these 2 I's, and then this I with this I, it would look exactly the same and wouldn't be considered a different rearrangement. Now, you can start by doing this. So again, let's think about it as filling 11 slots. So I have 11 slots to fill with these letters in this grouping, the letters of Mississippi. And then I'm going to apply the product rule, right? The generalized product rule. So the number of different rearrangements of these letters. The number of different rearrangements or the number of different permutations of these letters are the following. So my first choice is I'm going to choose, say, where the S's go. All right, I'm applying the generalized product rule here. So my first choice is I choose where do the S's go. Well, there are 11 slots. There are 4 S's. So that would be I'd have 11 slots, and I choose 4 of them. 11 choose 4, this is a combination, and I choose 4 of them to put an S in. So say here, 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 and there, right? And those aren't, I could have chosen any other 4, right? But there are 11 choose 4 ways to do that, what I just did. Pick 4 places where the S's go. Then the next choice, right? Now that I've selected where the S's have gone, done with the S's, how about I choose where the I's go? So the second choice, and again, just the product rule here. Second choice, the I's. Now, again, it's a generalized product rule where the number of ways one choice can happen depends on previous choices. Now, if I've already laid down these 4 S's, now there are only 7 slots to fill. And I have 4 I's to put in these 7 slots. So the number of ways I can select where the I's go is 7, choose 4. All right, so I lay down I's maybe here, here, and here and here. Again, of those remaining spots, I had 7 choose 4 different ways of doing that. All right. Next choice, right? So now I'm done choosing where the I's go, and once I've chosen where the I's go, now there's only 3 slots left. This, and this. And, next choice, third choice. Let's choose where the P's go. Where do the P's go? Now there's only 3 spots to fill now. You have 2 P's, so that'd be 3 choose 2. All right, 3 choose 2. And then finally, all right, let's say I put the P here and P there. And then finally, the last choice, now there's only 1 slot left. So I don't really need to fill this in because there's only 1 choice, but my last choice would be where do the M's go? All right, where do the M's go? Now there's only 1 M, right? And there's only 1 slot left, 1 choose 1. All right, now 1 choose 1 is 1. Now let me go through here and let me write out remember the formula for combinations, because what we're going to see here in a second is actually a much nicer formula. I'm going to simplify this. Right. Remember, this is 11 factorial divided by, and then 11 minus 4 factorial is 7 factorial times 4 factorial in the denominator. That's 11 choose 4 with the formula with the factorials in it. Times, and then 7 choose 4 would be 7 factorial divided by, and then 3 factorial times 4 factorial. Then 3 choose 2 would be 3 factorial divided by 1 factorial times 2 factorial. And then 1 choose 1 would be 1 factorial divided by 0 factorial times 1 factorial. Right? Just using the combination formula that you saw in a previous section. Now look at all the cancellations that can go on here. Got 7 factorial in this denominator, 7 factorial in that numerator. 3 factorial in this denominator, 3 factorial in that numerator. This is just 1. 0 factorial is also just 1. Right? So really, I don't need to write it. and then look what I'm left with. In the numerator, all I'm left with is this factor of 11 factorial. And then in the denominator, I have 4 factorial times 4 factorial times 2 factorial times 1 factorial. So you could also express it this way, product of combinations like this, or as these factorials. Now if you're typing this into a calculator, you have to go, put all this in parentheses down here, right? Now, 11, the numerator factorial, 11, that was the number of letters I had, right? 11 was the number of letters I was rearranging. And then look at all these factorials in the denominator. 4, 4, 2, and 1. 4 S's, 4 I's, 2 P's, 1 M. And notice I've got 4 factorial, 4 factorial, 2 factorial, 1 factorial. So it's like I'm rearranging the 11 letters, but then I divide it by 4 factorial for the 4 S's, 4 factorial for the 4 I's, 2 factorial for the 2 P's, and 1 factorial for the 1 M. So people tend to think that this is a much faster way of doing this than, doing all this counting with the combinations and making the choices that I did earlier. All right, let me show you the general formula. Now, let me actually punch this in. All right, so on the calculator, all right, let's pull this up. So I have 11, and then factorial, you hit math, go over to that PRB, down here, the factorial button. And then I'm dividing this by, now if you want to enter all this at once, you're going to have to put it in parentheses. But I'm going to do it one at a time. Divide by 24, which is 4 factorial. Divide by 24 again, another 4 factorial. And then divide by 2. All right, 2 factorial. And then divide by 1. Well, that's it. All right, so this is 34,650. So, the letters of Mississippi. There are 34,650 different looking rearrangements of the letters of Mississippi. There's one of them. Here, I didn't put the M in there. Here's another one. And there are 34,650 of these that all look different. Right. But this, I'm going to jump to this formula a lot. All right. So again, if you have n, all right, I'll just write that here. So if you have n objects, and n one of them are the same, n sub 2 of them are the same, all the way down to say n sub k of them are the same, and n1 plus n2 plus n3 all the way up to nk is equal to n, right? It's just the number of objects broken up into groups that look the same, kind of like the 11 letters broken up into the groups that look the same. All right, then the number of rearrangements, the number of different rearrangements, the number of permutations. All right, is this. The numerator is your number of objects, factorial, and then in the denominator, you have the product of all these, the numbers of objects that look the same, factorial. n1 factorial times n2 factorial, all the way to times n sub k factorial. All right. And this is exactly what happened up here with what I circled here. Right. Okay, and they write this up for us in a minute here too. Now you could also do that combination stuff. See how they did the combinations thing, and you can play the animation. But look at the formula they end up with, and it's the same way I was just showing you. So they write that here. Right. the number of distinct sequences, right? The number of different orders that you can put n objects in, where you have, n11s, n22s, nkks. You break them into groups as n factorial divided by, and then all in the denominator you have the product of n1 factorial times n2 factorial times all the way up to nk factorial. And they show you a little proof of kind of that here. All right, so how many ways are there to permute the letters or rearrange the letters in the word pepper? All right, so again, I'll pull that up on a piece of paper. So we got the word pepper. There are 6 letters, 6 objects. Now they're not all distinct though, right? They're not all different. So the number of ways to reorder them isn't just 6 factorial. There are 3 P's. So this would be like the N1. There are 2 E's, right? And there's 1 R, right? And these add up to 6. So the number of different rearrangements of these letters is 6 factorial in the numerator divided by, and then you have 3 factorial for the 3 P's times 2 factorial for the 2 E's times 1 factorial. Now 1 factorial is silly, right? That's just 1. And if you'd like, this is 6 times 5 times 4, times 3 factorial. So you got the 3 factorial down here. 2 factorial is just 2. And some things are canceling, right? The 3 factorial goes, 2 goes into 6 3 times, and you got, 12 times 5. This is 60. Or you could have punched this in a calculator, right? So there'd be 60 different looking ways to rearrange the letters of pepper. Now again, alternatively, you could have done, 6 choose 3. There's 6 slots to fill, and I choose where the 3 P's go. Then times, and then once I've put the 3 P's down, there's only 3 slots left, and I choose where the 2 E's go. And then when I put the 2 E's down, there's only 1 slot left, and then 1 choose 1 for where the R's go. Now 6 choose 3, that'd be 20, times 3 choose 2 would be 3, times 1 choose 1 is 1, and I'm getting 60 that way as well. Right? So you could also do it with this combination way. But either way you do it, it is 60 different ways to do that. All right? And how many different ways to rearrange the letters of the word happy? I'll let you do that one. All right, so I'll let you read this example here. All right, let's take a look at some more problems. All right. So suppose that 9 desserts are handed out to 9 kids. Each kid gets 1 dessert. There are 3 ice cream sandwiches, 4 cupcakes, and 2 bowls of pudding. How many ways are there to hand out the desserts to the kids? So again, think of it this way. Right, think of it this way. Think of it as a word. Now, you got these 3 ice cream sandwiches. I'll use I for ice cream sandwiches. And let's say they look identical. You can't tell them apart. So you got these 3 ice cream sandwiches, 3 I's. You got the 4 cupcakes. I'll use C for cupcakes. And again, suppose they came from the same bakery. You can barely tell them apart. They're not distinct. And 2 bowls of pudding. I'll use P for pudding. And again, they're maybe from the same, from the store. You can't really tell them apart. It wouldn't bother you if you got this one over that one, right? They're indistinguishable. So the number of objects here is 9. They said there were 9 kids. 3 I's, 4 C's, 2 P's, right? 3 ice cream sandwiches, 4, what did I say? Cupcakes, and 2 bowls of pudding. So the number of ways that, the number of orders that these could be put in, say kid 1 gets, and this would be kid 1, kid 2, all the way up to kid 9. The number of ways that these could be doled out to these 9 kids would be 9 factorial divided by, and then in the denominator, 3 factorial for the 3 I's times 4 factorial for the 3 cupcakes, the 3 C's, times 2 factorial for the 2 bowls of pudding. And that's 9 times 8 times 7 times 6 times 5 times 4 factorial. So that 4 factorial is gone. And then you've still got 3 factorial down here times 2. Well, 3 factorial is 6. And then 2 goes into 8 4 times. So this, 9 times 7 is 63. 63 times 20 would be 1260. So there'd be 1,260 ways, or you can enter this in a calculator, right? I don't care. 1,260 ways of, I didn't even look at it. They just want this. But that'd be 1,260 ways. All right, here, 15 kids arrive at a camp and are assigned a place to sleep. There are 3 different cabins, each of which can hold 5 kids. So how many ways are there to assign kids to cabins? All right, so again, you got 3 cabins. Say they're cabin A, B, and C. All right, cabin A, B, and C. So think of forming words. I could do this, say this is kid 1 through 15. Hey, kid 1, you go to cabin A. Kid 2, you go to cabin A. 3, you go to cabin A. 4, you go to cabin A. Maybe I'll send the first 5 kids to cabin A, and then the next 5 kids to cabin B, and then the last 5 kids to cabin C. That's one rearrangement. But I could also have sent the first kid to cabin A, the second kid to cabin B. As long as there were 5 A's, 5 B's, and 5 C's, that's all I wanted. Right? So the number of ways to do this would have been 15 factorial, right? There's 15 positions here, 15 kids. And then, divided by 5 factorial times 5 factorial times 5 factorial for the the cabin A, cabin B, cabin C that you're seeing. And looking back, that's all they want us to enter here. Okay. So again, rearrangements where, some of the objects are repetitions. Some of the objects look the same. All right. Okay, and then you got the additional exercises. Not all of these are assigned, but I would still recommend looking at all of them, practicing all of them, just to get better at the material, more exposure to it. And you can look at the solutions if you need to, right? But I do recommend, working on them first, trying to figure them out first before you look at the solutions. Don't just copy down the solutions. You're not going to learn anything if you're just copying solutions and not trying. And if you have any questions, of course, send me a message and I'll get back to you as soon as I can. And thank you very much for watching.